So, Breen, I think you are raising your hand.
I am indeed, yeah. Thanks for the talk. Really enjoyed it. Really interesting stuff. So my questions are around this unidirectional band gap you observed in the beam. I mean, could you say a bit more about so it just wasn't quite clear to me what the underlying mechanism for that was?
In the beams?
Yeah, exactly. Because at least I can see you've still got a system with time reversal symmetry, right?
Yes. Okay.
So
yeah. It's purely a I should have included the figure is in the paper actually. So if you look at the periodicity here on the right hand side, you see almost a normal periodic beam with thick and thin sections with a band gap happening at really low frequencies already. I would say around 4000 hertz. And if you look at the section here, you never have these thin sections overlapping. So because of the being out of phase of the thick sections on the top and the bottom, for this kind of unit cell, you reach a band gap around higher frequencies. I don't exactly remember where. And the band gap is very inefficient as well, simply because of the geometry of the unit cell there. So what you can see here is obviously there is time reversal. There's nothing nonlinear. There's nothing active going on. So the parity remains the same. It's purely an effect of the boundary conditions and the mechanical impedance. So waves do not want to propagate in this almost periodic section with a band gap here. So they're blocked here on the right-hand side. But the energy gets trapped in the left where they are allowed to move back and forth. And basically what is happening is that the section that feels the band gap is acting as a clamped boundary condition. So you're building up a mode that cannot penetrate beyond where the band gap is happening. So here you're clamped and here you get your local mode. And the funny thing is that you can actually see it. Here we're exciting on the right. You would see probably the more or less, no, it wouldn't be exactly the same if you excite from the left. This localization is way less pronounced because then the right hand side basically moves along with the motion of the point until where the waves can propagate. So you really need to excite at the location of the band gap. You pump the energy into the area where the waves are allowed to propagate and are allowed to build up a mode. And this is what you see.
So these plots, what's shown in these plots? What's the thing on the color bar?
This is simply amplitude. So this is the 2D FFT of the motion of this beam excited from the right. So it's the normalized amplitude for each frequency. So red means high amplitude. So here you have this main branch of the dispersion relationship where you have the typical parabolic for bending waves in a beam dispersion. And then as soon as you reach a band gap, you get this very noisy signal where you cannot discern anything simply because no waves are propagating.
Makes sense. Thank you.
Thanks. Maybe I can ask a quick question on this because I had also a problem to understand this two directions, the difference between the two directions. Have you also done the numerics on that?
Yes, it looks exactly the same, basically. I think the numerical results are also in the paper. I didn't want to put it here because they look the same.
So maybe sorry, let me just ask more precisely on these points that I don't understand in this plot. So you said you show with the color different amplitudes, but where is the amplitude taken on the beam?
Okay, so it's the method I was showing, but that was maybe too long before. The method I'm showing here. So in order to calculate a spatial Fourier transform, you need a periodic sampling of the motion of the beam along its length. So you do exactly the same thing as what you would do in the time domain. In the time domain, you have a periodic temporal sampling. and doing an FFT, you get the frequencies that belong to it. You do exactly the same thing in space. So you measure at all points along the beam. The length of the beam, well, pi divided by the length of the beam will give you the limit of the wave number. No, sorry, the wave number step that you can measure. And the spatial step, so the distance between 2 points, gives you the maximum wave number you can measure. And this is what you typically get. So that's why you get these fairly rough steps in the wave numbers here. This is because the total length of the beam is fairly short. So pi divided by that becomes fairly large. Now, if you then once again look back at the colors, there we go. If you don't do any kind of normalization, then you will see the vibration modes very clearly because they have a high amplitude. In this publication, I avoided this by, for each frequency line, normalizing the maximum amplitude to 1, so that also outside of vibrational modes, you get a clear image of this quasi-dispersion plot.
Okay, thanks. Do we have more questions online?
Can I ask a question?
Yes, Lorenzo, go ahead.
Okay, thank you very much for your nice presentation. Just on this picture, you spoke about these localized modes, right? Do you have any idea about how to predict the frequency of these modes inside the band gap? Just sorry, another question.
Yeah, no problem.
Do you think they are quite influenced by a change of topology in aperiodicity or not?
Yeah, really good questions. And the master student got really, I would say, insane by trying to do it. The problem is that for bending waves, we didn't find any analytical way to predict the location of the localized frequencies. The difficulty is mainly that this thing is completely asymmetric. So the thickness profiles are not the same on the top and the bottom. And we didn't find any decent way, especially also with the sharp corners. So if you would do like a sinusoidal wave on the top and on the bottom, we came close to something predictive. What we did is for local scatterers. I presented it once on a conference, but never in a paper, unfortunately. So if you have resonators or spring supports, then you can do some really nice analytical work based on free electron models in 2D lattices, basically. For the bending waves, we didn't. So the only thing we could do here was finite elements, to our big frustration. And then regarding your question of topology, yes, it really depends a lot on it. If you change, for instance, the initial phase here, or otherwise said, if you cut this superposition of periodicities at different points and you excite at a different point, you will reach different frequencies as well.
Okay. Another quick question. What you are estimating here, I see with this color, is basically the transmission coefficient. I mean, experimentally, something like that?
Not really. So transmission coefficient, you would basically take the excitation left and see what comes out on the other edge. This really takes into account the wave propagation along the entire length of the beam. So it's really a measure of, it's not really dispersion because it's not infinite, but how the waves propagate. So it's really a relation between frequency and wave number for this particular section of the beam. So it does give a bit more information than only transmission coefficient.
And you can estimate because you have a laser scan, right?
Yes, yes. Otherwise, it's very difficult, of course.
Yeah, because we did some different experiments. We haven't got a laser scan, so what we did, we estimate simply the transfer coefficient.
Which would also be nice actually in this case, because in this case you would have in the one direction, the traditional decrease, so a low transmission coefficient. And in the other direction, based on the amplitude, you can see here, you basically have an inflation. So you get an more than one transmission coefficient in terms of amplitude.
Okay. Thank you so much.
No problem. But if you have samples, bring them to us. We will measure them here and look what happens in between.
Okay. Okay.
Yeah.
Thank you so much. I will
No
send
problem.
a mail.
Good.
Hello.
Hi, Emil. You have a
Hi.
question too.
Yes, thank you so much for the interesting talk and these extremely fine measurements. It shows that you have control actually about over the spectrum and over the many things for these complicated systems. So I have a one recommendation, for example, for this beam. If you plot the spectrum, so now without resolving it over the wave number, just the spectrum, but as a function of this parameter R, then you will see that you get the Hofstadter spectrum, just the Hofstadter spectrum. And furthermore, there is a degree of freedom for this beam. For example, if you slide the top bar with respect to the lower part of the bar, lower half, then you'll see that okay, the pattern repeats itself after a while. So there is a degree of freedom. And in fact, it will be also interesting to plot what happens at a fixed theta by varying this degree of freedom. You will see that there will be edge states which do the usual pumping.
Yeah.
So you can literally pump vibrations from one end to another by just sliding this relative to another.
Yeah.
So I'm not sure.
So some of these plots are actually also included in the paper. We did a parametric study there, where indeed for varying R, you see the two edges of the Brillouin zone, and then you can also tell where this interaction or where this pumping becomes important. And same thing for the phase. Yeah.
So I should say that because this pumping is so simple, you say you just slide the two parts. Pumping of sound from one end to another was achieved using this setup, and in fact it was the first time to have sound pumped. How difficult will it be to have a beam with this reconfigurability built in and repeat such an experiment in this setting?
So yeah, we would have to have like 5 or 6 beams, or one very long.
No, I'm saying to do it dynamically. So I all at once
actively or
yeah. So you can render it in space, which of course that's very easy, but dynamically it's the challenge.
Yeah, absolutely. So there what I didn't show today and what we're also working on is changing the dynamic stiffness of structures using piezo elements, shunted piezos, where you can locally embed or you can basically program which parts you want to be you want to have a very low stiffness and other parts that have a very high stiffness. If this works, but then you need several piezos that are all tuned independently. If you can tune them statically, you could also program them to have an. So I think there is quite some work in this field from I know the people in Lille are working on these piezo structures that are actively controlled. Also in Milano, there is someone who does this kind of work. The main problem for us would be practically that we don't have good electronics engineers in our lab. So we have a lot of physics, material science, mechanics, but not really electronics. So that would probably be the bottleneck.
The challenge here, however, is the damping. To move the signal from one end to another, you have to do it quite fast. So in other words, the pumping has to happen about 10% of the frequency, and you simply cannot do that by electronics. You really have this sliding is actually the solution, because you can slide it extremely fast.
Yeah. Okay. Yeah, it's would be an interesting approach for sure.
To have some somehow to interconnect the beams and still yet to leave this degree of freedom.
Yeah.
Okay. Do we have more questions? Just looking at the audience. Apparently not. So let me just ask you a last question regarding this general framework of quasicrystals. Is there any method to get or to define effective properties of quasicrystals from the dynamical point of view? Because anything that you would use like this approximates or anything, this is always like you are making a truncation or something.
Yeah.
Is there any work recent? Of
I actually, I don't know. It depends a bit on the frequency range. So obviously at low frequencies, you can homogenize fairly easily. Already homogenization for bending waves is always tricky because you have the coupling of longitudinal and shear waves. And as soon as you have dispersion with negative slope, it becomes a lot of homogenization schemes have difficulties there. So honestly, I don't know if people are working on it, or because it would definitely give us a good tool to have better control, right? But we don't do it, and I don't know any publication where they tackle this problem.
Can I ask one more question?
Yeah, go ahead.
So how do we bring these systems to real applications? I will, especially that you are working in this institute and interacting with so many people, do you see some unique applications for the systems?
So typically what I hope from the one-dimensional case is this remark that I put here. So that we can get low frequency band gaps with a much higher static stiffness. So typically, in order to reach low frequency band gaps, you need either something that's very heavy or that's very weak. I am hoping that in some applications, and now we actually start going to collaborate with someone, where we could show that doing maybe not fully aperiodic, but a combination of two periodicities might be beneficial, because we get a higher static stiffness, so your structure becomes more stable. In a 2D case, we're more at the moment more at a conceptual stage.
Yeah, it's good to know that somebody's thinking.
Yeah. So that's the philosophy of Empa, basically. Their slogan is the place where innovation starts. So we should do work that we can show industrial partners and that trigger some interest.
Yes, because it's very important. There are so many demonstrations, but the time of demonstrations, it's kind of peaking. Now we really need badly real applications to continue saying that these are interesting and possibilities. Yet we
I couldn't agree more.
We couldn't deliver some application.
Yeah.
All right. I see no other question from the audience. So I would like to say thank you again for the nice talk.
My pleasure.
Thank you.
Everything was recorded and it should be online and together with a DOI that anyone present here would like to cite. You would be welcome. You can just cite it as a paper. and it should be available in the next few days. So
thank you very much.
Thank you very much, and see you next week.
Bye.
Thank you. Bye.